and my k. And if I decide to stretch this out to make it up, now it's changes my to positive or negative or more and more negative as I get steeper and steeper. So you can see these controls, how I can pick it up and move it around, affecting my h and my k. Now let's take a look at some higher order polynomials. Polynomials are continuous and they're always smooth. They have no breaks in them. One simple reason for this is that you can take any real number and take it to a power and multiply it by a number and add or subtract it. So there's nothing that you're not allowed to put into a polynomial function. So the domain is all real numbers and you get this continuous graph. You also are not going to have any sharp turns. As I said, it's going to be smooth. It's always going to have nice smooth turns as opposed to sharp turns like an absolute value. This is a basic cubic function. Here's our vertex. It's an odd function, symmetric about the origin. Domain and range are both all real numbers. This is some transformations of some basic functions. So flipping over x to the fifth, or moving x to the fourth up by 1, or moving x to the fourth to the left by 1. But this leads to the idea of end behavior. What's going on with these higher order functions? And so let's take a look at end behavior. Now the thing about a polynomial function, ax to the n plus bx to the n minus 1 and so on, is all we care about for end behavior is the leading term. And let's say we had something like 2x cubed plus 10 to the 17th power x minus 10 to the 88th. Well, if x isn't very big, these terms obviously have a huge part to play in what your y value is. But as x goes towards infinity, all we care about is the highest degree term, because that's really going to determine what's going on. So just to take the four cases one at a time, looking at the leading term, we can have a is positive or negative and n is odd or even. And so if n is odd and a is positive, for example, just 2x cubed, because all we care about is the leading term, if x was negative, negative cubed is negative, times 2 is negative, so I would be down here somewhere. If x is positive, positive cubed is positive, times 2, I'm up here somewhere, and so I get some sort of shape. In this case, a is positive and n is even. Well, now if I take a negative number, a negative x value to the 6th power is positive, times positive is positive. Positive x value over here somewhere, am I down here or up here? Well, to the 6th power is positive, times a positive is positive, so I come down, do some stuff, go back up. The calculus is what you need to figure out more what's going on here. The other two cases, when n is negative, well, basically things are flipped over. I'll start up here and down here for n, a negative, n odd, and if a is negative, n even, well, then I'm flipped over this way. So that tells you your end behavior, what's going on when x goes toward negative infinity and positive infinity. As far as getting things in between, well, we can figure out intercepts, x-intercepts by factoring, y-intercepts easily enough by just evaluating at x equals 0. To find some of these spots, maximum, minimum, so forth, that requires much more analysis. Here's a few more examples of end behavior. F of x equals negative x cubed plus 4x. We can ignore the 4x, and for negative x cubed, we'll start upper left and bottom right. For this quartic, again, we ignore all the lower degree terms. We just look at the x to the 4th, and if x is negative to the 4th power, it gives me a positive, so I'm up here. If x is positive to the 4th power, I get a positive, so I'm over here. So I'm going to start upper left and upper right, do some stuff in between. Of course, this is an even function, so it's symmetric about the y-axis. There's other things you can get out of this. For this function here, leading term is x to the 5th. I'll start bottom left and upper right. This is an odd function, so I'm symmetric about the origin. So let's take a look a little bit more closely at the evolution of this. Here we start with a constant function. And so then if we decide to move this up in degree, well, here we are, just our constant functions. So this is x to the 0 power, basically. And then what we can do is to start to adjust this. So our linear piece is e. So let's change that. So now we have our linear function. Our quadratic is d. So now we start to get a quadratic. So there's our end behavior there. Our cubic part is our coefficient c. So you can have a max and a min for a cubic, or you can just have it this what's called a point of inflection. So there's a classic looking cubic. Then we can adjust our coefficient on the quartic, and now it's this way. Looks a little bit like a parabola. It's very difficult to tell the difference unless we make further adjustments. Here, now if I change it like this, it looks obviously not parabolic. And then we can even make this back into a quintic, a 5th degree, and now once again we're starting bottom left and upper right. I can make it negative, and we'll go the other way now, upper left to bottom right. Okay, now looking at some of the zeros, more in particular, and getting on to graphing. Well, first of all, some vocabulary. Zeros, solutions, factors, x-intercepts, they all basically mean the same idea. But one thing that can be very useful when you have a factored form of a polynomial is what's called the multiplicity of the factor. If you have a root of even multiplicity, it's going to bounce off the x-axis, and if it's odd multiplicity, it's going to go through. There are very distinct reasons for this, but I'm just going to go through some of the results right now, not the reason for why an even root bounces off and an odd multiplicity root goes through. So this is how we can use that fact. So let's say I have this factored polynomial x plus 1 squared times x minus 1 cubed times x minus 4. Well, I know I've got intercepts at -1, 1, and 4. I know I've got a y-intercept at positive 4, because if I plug in 0 for these x's, I'm just going to get 4. I know my leading term would be 1x to the 6th if I were to multiply this out. So I know I'm going to start over here. I'll be starting in this area over here, and I'll be ending over here. Okay, let's go down to this number line for a moment. So I've got x, f of x. I put in my x-intercepts. The y value is 0 at each of those. Now, if I take the number to the left of -1, like -100, and I plug -100 in here, I'll have a negative squared is positive, a negative cubed is negative, and a negative minus 4 is negative. So that's positive, negative, and negative. So I'm going to be positive, which makes sense because we know from our end behavior we should be up here. If I pick a number between -1 and 1, like 0, I would have a positive squared is positive, negative cubed is negative, negative is negative, and I get a positive again. And so it would seem as if we bounce off here, and that makes sense because look, it's an even root. 2 is an even number, so I'm going to come down, and I'm going to bounce off, go up to here. I'll come back down to this spot. Now, this is to the third power, so I'm going to go through, and so I flatten a bit, and then I'm going to come down. And when I get to 4, I'm going to go through again because that's to the first power. So you can continue with this number line. Try out, say, the number 2. If you plugged in 2, it's between 1 and 4. I'd have a positive, and a negative, so it's negative. And as you can see, between 1 and 4, I'm below here. And then after 4, I'm above the x-axis. One thing to note is that besides the fact that the even multiplicity roots bounce off and the odd ones go through, the higher order ones flatten out more. This is flatter as far as a intersection through the x-axis than this would be, and that's again because as you get numbers between 0 and 1 to higher powers, they actually get smaller, not bigger. So we're going to flatten more if we have a higher degree. Another example, x squared times negative x minus 4 times x minus 2 to the 4th times x minus 3. Well, first I'm going to factor a negative out of here, so this factor becomes negative times x plus 4. If I multiply the whole thing out, I get negative x to the 8th. So I'm going to start down here, end down here. Okay, here's my number line again. So I don't even really need it though, because at this point I know that at -4 I'm going to go through. It's to the first power, so I go through. At 0 I'm going to bounce off. It's an even root. At 2 I'm going to bounce off again, but I will flatten some. And then at 3, I'm going to go through. And you see that I end up down below as I knew that I had to. So here's just a bit of a review of what I've been doing. I think about the leading coefficient test to give me an idea of where it starts and ends. 3x to the 4th is the leading term. Try to find the zeros if you can by factoring. Think about if you're bouncing through or bouncing off or going through, depending upon the multiplicity of your root. Plot a few more points perhaps. When we get into calculus, though, you'll be able to find much more accurate points that are useful, like local maxima or minima, and then try to draw the graph. And so that's what they're doing in this particular example. And you see they've got the end behavior, they have the intercepts, and then you get some behavior. And notice that this is third degree, not just first degree, so we flatten at 0 much more compared to 4/3. Same idea here, negative 2x cubed is your leading coefficient, some factoring, so even multiplicity at 3/2, odd multiplicity at 0, and so there's our cubic. Lastly, we have what's called the intermediate value theorem, And this is something we generally have been taking for granted thus far because so many of our functions have been continuous, though they won't be so much so later on. But for now, if you have a continuous function, the idea behind the intermediate value theorem is you have this interval from a to b, which defines this y interval from f of a to f of b, and the intermediate value theorem simply says that if you pick any y value between these two y values, it will correspond to at least one x value between these two x values. Now, what that allows you to do is to try to find x-intercepts of a polynomial by sort of zeroing in on it, because in this case we know that there is this value c between a and b that gives you this y value, but if f of b is, say, positive and f of a is negative, then we would know that there would be at least one place between a and b which would give us a place that was 0, and that's what's going on in example 9. We have this function. We're trying to find a place where we know there's an x-intercept, that is where there's a 0. So if we can figure out an x value which gives us a negative y value and another x value which gives us a positive y value, we can conclude that there must be an x value between the two which gives us an x-intercept or a 0.